Good afternoon. I'm Suyang from UCL, and I'm glad to be here for this meeting. And I'll represent all the co-authors from UCL and University of the Cambridge for this presentation entitled "Geometric Model of the Hydropower Plant: Foundation Step Towards Creating a Hydropower Digital Twin." So this work was carried out by two teams together, and here's the outline of our presentation today. So let's begin with the background first. The EU's clean energy transition goals requires at least at a 55% reduction of the greenhouse gas emissions by 2030. And the hydropower plant and other dispatchable renewables are expected to triple in the capacity, reaching over 125 gigawatts by the 2030. So to achieve these targets, digitalization can play a key role in enhancing the compatibility of these existing hydropower technologies and to overcome the operational and environmental challenges. So our project is built around the DHydroFlex cloud platform, which is an EU-funded research project, which serves as a backbone for the integrating of all these tools with the digital twins. And this platform includes hydro unit digital twin, a dam digital twin, and a decision support tools for the hybrid, the hydropower plants, the weathers, and the flow and the production forecasting tools, and even the biodiversity index. And yeah. So now the problem we are addressing is that how to enhance the sustainability, the flexibility, and the efficiency of the existing hydropower plants across the Europe through the digital technologies. And the project aims to develop a comprehensive toolkit of the digital solutions, including the digital twins of hydropower plants, AI-based predictive maintenance algorithms, and some other biodiversity monitoring tools. So these tools will be validated in real-world hydropower plants across 5 Europe countries, and the expected outcomes are improved for the operational efficiency, reduce the maintenance costs, and enhance the environment sustainability, and some others. So now let's move to the highlight of specific objectives for this DHydroFlex project. First, we aim to design and digitalize the hydropower plants of the future based on the DHydroFlex Hydropower 4.0 toolkits. This will enable a real-time system management and remote monitoring of the hydropower plants. And second, we will develop IoT and the digital twin technologies along with the AI-based technologies for the data ingestion, analysis, and advanced forecasting, including the hydropower plant production, weathers, and others. Thirdly, we will work on the novel sensor-based modeling and image processing algorithms that will help to reduce the impact of the hydropower plants for the environment. First, we want to demonstrate the applicability and the value of this platform. We will do this through the industrial and real-world application across Europe, testing on different type of climate zones, different type of dams and the conditions, operations. So moving on to the methodology and the key innovations here, why did we choose the geometric digital twin? Mainly, it will allow us to create an accurate 3D models of the dam structures for better understanding of the dam, of the hydropower plant, and do some analyze on it. So it will improve the inspections, maintenance of planning, and risk assessment with these spatial insights, and support the design, construction, operation, and even the renovation phase with the up-to-date geometry. So the workflow of our geometric digital twin involves mainly the 4 key steps here. The first one is data cleaning first, which removes the noises, align scans, and standardize the formats for sure, and segmentation to identify and isolate the structure components. And then we do the object relation extraction to determine the spatial relationships with the components. And finally, is a mesh generation to convert all this data into, process the data into a high fidelity 3D mesh ready for the integration and the work after that. So as you can see, there is regarding the data sets, we have used some open source data from the Rushboard Dam in New Zealand, and also we have some real-time, and we have some real data from the Pavlos Dam in Greece as for main demonstration sites here. And these slides show the segmentation labels for these the internal and external point clouds, and a comparison between the public data sets on the left and our own data sets on the right for these project data sets. Yes, this is some results we have been done for the internal side. So next one is the segmentation algorithm. For segmentation, it breaks down the complex dam geometrics and into recognizable shapes such as the planes and the cinders. So why we choose the RANSAC? We choose the RANSAC algorithm for this one. It's because it's more robust to the noises and the outliers, and which is ideal for imperfect scan data and some small data sets, especially like the scenario for the dam. And here you can see this is some results of the shaping feeding and for the point cloud, and a corresponding index value graph into the quality of the segmented feedings. And next one is about the relationship graph. Beyond the segmentation, we also do some work on to establish a relationship graph for the whole dam. And this will add the semantic understanding, and not just by what components they are, but what are the relationship with them, and the interact with each part of it. So the types of relationship mainly include like adjacency and alignment, containment, and connectivity. So using the bounding box analysis and the the surface proximity, and also some normal vectors comparison, we generate the connective hierarchy model for all these components in one dam, as you can see here. And so then we convert all these point clouds into mesh. Point clouds are understandable dense, while meshes are more structured and lightweighted, and compatible with the simulation and visualization tools. So we use the BPA algorithm with which will preserve a sharp features for all these point cloud data. And then the output is a clean, structured, mesh-ready downstreams. That would be really helpful for rendering or using BIM for integration. Of course, we got some limitations for our work here. There's a lack of open source data first, especially for the dam. As you know, it's not a usual scenario as we can see in our real life. And the hydropower plant components, which is really complex. And the second one is that the upstream phase of the dam is often submerged under the water. So it will lead into some incomplete models. And finally, due to the diversity of the dam's architecture itself and the construction methods, like it's really hard to apply a one-fits-all for the segmentation or modeling pipeline. So for the future work, we plan to introduce deep learning-based segmentation to replacing the rule-based method like we have already introduced the RANSEG, to learn more about the complex and irregular components for the data of the dam. So we also enhance the mesh generation by using hybrid approach to create a water-tighted and higher fidelity mesh at a lower file size, which will be really helpful to improving the handling of the occlusions and the noisy data. So thank you so much. Thank you so much for your attention and learning. Thank you.
Thank you very much.